Good evening, all of you. Is my voice clear to all? So let us begin our today's session. So, any queries for anybody on the previous class? What we discussed? Tell me. Any questions you have? So what is the problem with constant term? Right? Suppose you have taken the constant term. Then what happens if you consider the condition of an ideal? Say, I have taken that suppose u of x contains all the polynomials of this type. Now, as per the definition of ideal, so this is f of x and this is u of x. For every polynomial in f, when you consider one value in u, one value in f, the product must belong to u. So if I take a polynomial in u of x and any other polynomial f of x belongs to f of x, then while considering the product, this value must belong to u of x. Accepted? Yes or no? The ideal second condition. There we will get the problem. You cannot give guarantee that always the same constant term will belong to u of x. That is a problem. Especially if you take the multiples of a particular value, then you get the problem. However, this type of situation will not affect if you deal with the rings under modulo operations. The rings under the modulo operations. There we will consider constant term also. No problem at all. Similar kind of problem we will deal while doing the class. Okay? Right. So any other queries, please? Any other queries? Then let us discuss some other concepts. So, if R is real numbers, so we have to show that R of x by generated by x square plus 1 is isomorphic to C, the set of complex numbers. So this is our problem. Please take a note of that. So it is given that R is the complete real number system. You have considered the polynomial ring R of x. You are going to show that R of x by multiples of x square plus 1. This is the quotient ring. This is nothing but isomorphic to the complex number system. Okay. Here you can observe that you are considering the multiples of the polynomial x square plus 1. Accepted? Here we have consider the constant term also. So here you will get all the multiples of this polynomial. It is an ideal as per the data given. Did you observe that? So this is our problem. We are going to show that these two are isomorphic. So whenever isomorphic situation arises, always we make use of the fundamental theorem. So what the fundamental theorem states? Whenever two rings are given to us, we need to construct a homomorphism between them, and sometimes it is onto also. Then by applying the fundamental theorem, domain by kernel is isomorphic to codomain. So similar kind of situation we have to build here so that these two will become isomorphic. Okay, the strategy of the problem. Now I am going to define a function. Let me say I have taken phi from r of x to c. Now how to define the function here which should be a homomorphism? As we know that c contains all the complex numbers and r of x contains all the polynomials. So how to define that? So whenever you take a polynomial f of x belongs to r of x, you define that phi of f of x is equal to f of I. It is nothing but simply in place of x, you substitute I, the resultant is nothing but a complex number. So domain contains all polynomials, codomain contains the complex numbers. This is the way we define the function. Please take a note of this one. And I will say that if you define the function, it will become automatically the homomorphism. You can cross verify that. There is no doubt at all. And it will become onto also. Because if you take any complex number system, any complex number on the right hand side, say I have taken a plus ib. What could be the corresponding polynomial here? So the polynomial what I am taking is bx plus a. So this is the polynomial in the domain. So f of I, if you consider this is nothing but bi plus a, our value will come automatically. Did you observe it? So if you define the function in such a manner, it is onto homomorphism trivially satisfies, you can cross verify that. If you are interested, let us verify for that also, or you can do very easy. Now, by fundamental theorem of homomorphism, we can say that domain by kernel is isomorphic to codomain C. Now, it is our interest to say that what is the value of kernel, and from the problem itself we have to prove that kernel is generated by this value. Okay, now let us write the definition of kernel here. Kernel phi is equal to set of all polynomials in the domain such that phi of f is equal to 0. Here 0 is nothing but the 0 complex number. So it is nothing but set of all polynomials f belongs to r of x such that f of I equal to 0. So whenever you write an arbitrary polynomial, say a naught plus a1x plus so on plus an x power n plus so on. Whenever this kind of polynomial you consider, you are substituting I in place of x, the result is nothing but 0. So our interest is, I want to show that you cannot get the first degree polynomial in kernel. So if I am able to prove that you cannot get a first degree polynomial in kernel, it means that kernel must contain always second degree polynomials and higher degree polynomials. Accepted? If I am able to prove that kernel should not have first degree polynomials, then the possibility for kernel is it will contain the polynomials of degree 2 and higher. Accepted? Because R of x contains all possible degrees for all polynomials. Isn't it? Are you getting the context or not? Now, let us consider a first degree polynomial. Let us say there is a polynomial, say px plus q belongs to R of x, whose degree is 1. Now tell me, how do we confirm that this is the degree of the polynomial? Say, how do we confirm that this is the degree of the polynomial? In other words, if you say that f of x is a polynomial of degree n, it means that while considering the powers, x power n coefficient is not equal to 0 and n is the highest power in that polynomial. Accepted? Right? So similarly, if I say that this is a first degree polynomial in R of x, it means that by default the coefficient of x p must be not equal to 0. Am I correct? So if you say that any first degree polynomial belongs to kernel, that means say if the polynomial px plus q belongs to the kernel. As per the kernel definition, while substituting I, it should become 0. That means pi plus q must be equal to the 0 complex number. So if you equate the real part as well as the imaginary part, both sides, so q will become 0 and p will become 0. But this is a contradiction, because you have taken the first degree polynomial means p by default not equal to 0. Otherwise, we cannot say that it is a first degree polynomial. Am I correct? Yes or no? Therefore, kernel phi will not contain any first degree polynomial from this discussion. Now what happens? We need to give a clarity that kernel will contain second or higher degree polynomials. That means it is enough for us to show that kernel contains at least one second degree polynomial. Say, isn't it? That polynomial we need to show. So as per the problem, this is there in the denominator. So let us verify that the second degree polynomial x square plus 1 belong to the kernel or not. Let us verify that. So if you consider f of x square plus 1, so substituting the formula, it will be I square plus 1 equal to 0. Accepted? I square is nothing but minus 1. Hence, x square plus 1 will belong to the kernel. Did you get it or not? Now what happens? We know that the real numbers is a field. The real numbers is a field. So, if you consider R of x, it is the polynomial ring over the field R. In yesterday's class, we discussed that whenever you write f of x, it is a principal ideal ring. If you take the set f as field, the polynomial ring f of x is the principal ideal ring. And another interesting thing is there that while calculating the principal ideal, we observe the technique that it is generated by the smallest degree polynomial. Accepted? In the proof of it. Did you get it? There we used that g of x is the polynomial in the ideal u having smallest degree. Using that technique only, we have proved that the ideal u is generated by g of x. Now what happens? If you consider R of x by kernel, we know that always kernel is an ideal. And if you consider R of x here, R of x is a principal ideal ring, so that kernel phi is a principal ideal ring. So we should know that what is the polynomial having the smallest degree in kernel. There may be many polynomials having the smallest degree, but we should know at least one polynomial of smallest degree. Just now we proved that kernel is not containing any first degree polynomial, and we proved that x square plus 1 is the polynomial which is in kernel, whose degree is 2. So kernel contains the smallest degree 2, and the polynomial is nothing but x square plus 1. And immediately I am confirming that kernel is generated by the polynomial x square plus 1. Because I know one polynomial, right? So if you consider the generators, always it will belong to the kernel. There is no other option at all. Did you agree? So kernel is generated by x square plus 1. Now another interesting thing comes. So by fundamental theorem, R of x by kernel f, kernel phi is isomorphic to C. I have taken that kernel is generated by the polynomial x square plus 1. So R of x by generated by x square plus 1 is isomorphic to C. That is the conclusion of the problem. Clear to all? Please tell. Please take a note of that, then we will discuss other things. Any questions or any doubts for anybody? Shall I continue further? Right. Now, let us take some small problems which will enhance our concept and knowledge. Show that Z3 of x by I, where I is the polynomial generated, I is the ideal generated by the polynomial x square plus x plus 1. So our thing is, it is not an integral domain that we have to show. So I have considered the quotient ring Z3 of x by I, and I want to show that it is not an integral domain, and the ideal I is nothing but it is the generating set given by the polynomial x square plus x plus 1. Please take a note of that. Now coming to the context, what property we need to check so that it is not an integral domain? That is a good idea. I is not a prime ideal. That is right. Any other technique? If you go with the definition of an integral domain, if it contains no zero divisor, if it has no zero divisors, it will become integral domain. If it contains zero divisors, it is not an integral domain as per the definition concerned. Accepted? So we have to show that I should have two elements or one element such that the product, if you consider, is 0, but the element is non-zero. So what is meant by having zero divisors? A not equal to 0, B not equal to 0, but product equal to 0. Either you can take the same element or different element, that doesn't matter. You have taken the non-zero value, but the result is a zero value. If such type of situation arises, means it is having zero divisors, therefore it is not an integral domain. Accepted? Right. Now, if you consider the ring Z3 of x, so here you are considering any polynomial where coefficients are precisely 0, 1, 2, because this is nothing but the set Z3. Whatever the polynomial you write, the coefficient must be having the values 0 or 1 or 2. Now I consider the polynomial x plus 2 belongs to Z3 of x. So as per the quotient ring definition, x plus 2 plus I belongs to the quotient ring. Now I say that this element is a non-zero value, but if you consider the product, it is giving 0. So if you consider x plus 2 plus I dot x plus 2 plus I, I have considered the square of the value. So how do we multiply the cosets? We simply multiply the respective values. The set will remain same. So this is nothing but x plus 2 whole square plus I. As per quotient multiplication, how do we do that? A plus u dot b plus u is nothing but ab plus u, the quotient multiplication. So if you expand this, it is nothing but x square plus 4x plus 4 plus I under modulo 3. Because for the ring Z3 of x, we have the modulo operation 3. So what is meant by modulo operation? While writing the polynomial, whenever the coefficient is equal to 3 or more than 3, we need to consider the remainder. So this is nothing but x square plus x plus 1 plus I under the operation modulo 3. So this is nothing but I as per the given thing. So the result is equal to I plus I, nothing but I. So precisely I is the zero element in the quotient ring. So what happened? This quotient is belonging to the quotient ring and it is a non-zero quotient. So if you multiply with the same element, I am getting 0. So it is having 0 divisors because elements are non-zero but the product is 0. Hence it contains 0 divisors so that it is not an integral domain. Okay? Please check the solution part. Yeah. What I am saying is, this is the definition of 0 divisors. Accepted? So in place of A and B, you can take the same element. If you take both the values as A, so A square should become 0 when A is equal to 0, when A is not equal to 0, as per the definition concerned. Accepted? So if you take that, this is the value A in the quotient ring Z3 of x by I, and this is a non-zero value. Elements are non-zero, right? But if you consider its square, you are getting 0 here. So element is non-zero, but the product is 0. So it is having 0 divisors. Therefore, it is not an integral domain. Clear now? So similar kind of problem, let us take one more. So can I erase that? Okay. So let us take the ring Z2 of x. So I am writing all the polynomials with coefficients 0 and 1 only. Because Z2 is nothing but 0, 1. The operations are addition modulo 2 and multiplication modulo 2. So you consider the ideal generated by x square plus 1. This is the ideal I have taken. Now the question here is, we have to show that it is not a prime ideal. This is our question. So I is not a prime ideal. So how we are going to prove that? So what is the definition of prime ideal? Whenever you consider two values in the ring, if the product belongs to the ideal, then at least one of the values must belong to the ideal. Then only we say that it is a prime ideal. Accepted? The definition of prime ideal. Whenever you say that A, B belongs to I, then either A belongs to I or B belongs to I. This condition must be satisfied by the ideal I. Then only we say that it is a prime ideal. Accepted all? Fine. Now, I am considering the value that we know that so if we have taken the value x plus 1 whole square, let me say. I have taken the value x plus 1 whole square. So if you expand this, this is x square plus 2x plus 1. So basically, x plus 1 is a polynomial in the ring Z2 of x. And I have considered x plus 1 whole square. So this is the expansion. It is nothing but, since you are applying the operations under modulo 2, this value is 0. It is nothing but x square plus 1. So this value belongs to ideal generated by x square plus 1. So what you got it? X plus 1 whole square is nothing but x plus 1 dot x plus 1. And you are saying that the result is belonging to the I because this is I. But we definitely say that none of the values, either x plus 1 or this x plus 1, is an element of I. These are not at all elements of I. Because you are having x square plus 1 is the primary element. So we say that x plus 1 definitely does not belong to x square plus 1 generated by. So elements are not belonging to the set, but product is belonging to the set. So it is totally against to the definition of prime ideal. Therefore, this is not a prime ideal. Okay? Whenever the product belongs to the ideal, one of the elements must belong to the ideal. This is the criteria for prime ideal. So here, the product belonging to the ideal is accepted. But in that product, no element is belonging to I. X plus 1 is not at all a member of I. Accepted? Therefore, it is not a prime ideal. Is it clear or any questions? Shall I continue? Okay. Now coming to the definition of yes, why not? So if you want to show that it is not a prime ideal, then you simply show that Z2 of x is not an integral domain. That means you should have a quotient ring, right? So you consider the quotient ring Z2 of x by generated by x square plus 1. As you have taken that this is I, so you consider that Z2 of x by I. Now, Just like the previous problem, I prove that it contains the zero divisors. So what it means, I have taken the non-zero polynomial, non-zero coset in Z2 of x by I. You consider its square just like the previous problem. So it is nothing but x square plus 1 plus I, nothing but I plus I is equal to I. Now what happens? Element is a non-zero value, but product is a zero value. So the quotient ring is having zero divisors. It is not an integral domain. Therefore, the ideal is not a prime ideal. That is also correct. This is the other approach. Why I have taken different approaches? Because for the same problem, two methods are there. So I want to discuss about the methods so that among the two I have taken different problems. That is my actual intention. You can observe that this problem is solved in two methods, right? Previous method and the current method. That's it. You can use the technique of any. You can use the technique of prime ideal or you can use the technique of integral domain. So if you have noted this, I want to give the definition of unique factorization domain. Right? In a short note, we call them as UVFD. So with regard to the context of UVFD, whenever you consider some results based on UVFD, the proofs are very lengthy. So there is no need to learn all the proofs with regard to exam point of view. Because we cannot give guarantee that definitely a result will be asked on UVFD. Because majority of the results are asked on PIDs, Euclidean domains, etc., etc. Now here we are going to build a small relation or connection between unique factorization domains and PIDs, etc., etc. by taking some examples. So questions based on the relation are asked in UPSC. So let us deal with that part. Because it's a very lengthy thing. You cannot give guarantee that a specific result will be asked on this part. I will deal with some standard results which are useful with regard to exam point of view. And I will give the definition of unique factorization domain. Right? Can I continue? Now, from the very word, we can understand that domain stands for integral domain. Unique factorization means where we can configure the elements or where we can factorize the elements in a unique way. Right? So how the definition comes? You consider an integral domain, say D. We say that it is a unique factorization domain satisfying the following properties. One is if you take any non-zero, non-unit element, then we can write it as product of irreducible elements. Can be written as product of a finite number of irreducible elements. And second thing is the factorization is unique. So what is meant by unique factorization? If you say that if you take an element A, it has two factorizations. Say A is equal to Q1, Q2, so on, Qm, and A is equal to P1, P2, so on, Pn. Let me say. Then this is a kind of factorization, this is a kind of factorization. So in this factorization, each element here must be an associate of some element here. So each Pi must be an associate of some Qj, and vice versa. If this is the associate of this, by default, this is the associate of this. This we call it as unique factorization. Now see what we are taking. If you take an integral domain, in that you remove the zero element, you remove the elements having inverse. Those elements we call them as units. So excluding these kind of elements, you will have other elements. So those elements are non-zero. Those elements will not possess inverse. If you pick up such type of element in the integral domain, then it is possible for us to write the element as a product of a finite number of values, and each value is irreducible. So what is the meaning of irreducible? You cannot reduce it into further. Further reduction is not possible. That is the thing. And we are saying that such type of factorization is unique. So what does this means? Whenever you say that an element has two types of factorizations are available, then on this side each value is an associate of some element here. So each Pi is equal to a multiple of some Qj, where this is a unit. This is the actual definition of unique factorization domains. Clear? Any doubts? Are you clear or not? Right. Now, immediately some questions arise into our mind. How do we check for the example of UFD? The very fundamental thing is, you consider any field. Every field is unique factorization domain. Because if you talk of a field, every element will possess the multiplicative inverse. Accepted? Yes or no? In a field, every non-zero element will possess the multiplicative inverse. Right. Now, coming to the concept of unique factorization domain, UFD, you are writing or you are factorizing the elements which are not having inverse. So element which will not possess inverse, for those elements only we are saying that factorization is possible. But if you take the case of field, every non-zero element by default will have the inverse because it is a field. So there is no need to write the factorization further. There is no need to write the factorization because every element is having inverse there, right? So every field is by default unique factorization domain. Clear? The fundamental example. If you take another example, let me say I have considered our ring z plus dot, the set of integers. We know that the set of integers is an integral domain. And I will say that it is an UFD. Now coming to Z, can you mention what are the elements having inverse in Z? What are the elements having inverse in Z? One and minus one. Accepted? One has inverse one itself, minus one has inverse minus one itself. So if you take any other element like 2, 3, 4, so on, all these are nothing but non-zero values and non-units. So whatever the integer you consider, by default, we can write it as a product of finite number of values. Because if you take the value, say, I will take the value, say 36. This is nothing but 4 into 9, nothing but 2 square into 3 square. So this is nothing but 2 into 2, 3 into 3. Accepted? Yes or no? So every integer can be written as product of primes. This thing we call it as fundamental theorem of arithmetic. Agree? In the school level we learn this. Fundamental theorem of arithmetic states that if you take the integer, always we can write it as product of prime numbers. Now see, can I say that 2 is an irreducible element? 2 is an irreducible element because you cannot reduce 2 further. You cannot write 2 as product of 2 distinct values. Agree or not? So you can check the thing that for 36, if you consider the representations 2 square into 3 square, this is one type of representation, or 3 square into 2 square. This is another kind of representation. So whatever the order you consider, you can write it as every number as a product of a finite number of irreducible elements. And we know one more interesting thing that Z plus dot is a principal ideal domain. Whatever the ideal you consider, it is by default a principal ideal. Agree? So from this very context, we can say one thing that whenever you take a principal ideal domain, it is always a unique factorization domain. Every PID is a UFD. And UFD need not be a PID. So example is not important. UFD need not be a PID. That we can understand here. So since we are talking about the factorizations, whenever you take any two elements in the UFD, we can find the GCD as well as we can find the LCM for it. So another interesting thing we can share here is with regard to Z plus dot. And as we know that it is a principal ideal domain, I think in the yesterday class or previous class, we have done one more thing that in a principal ideal domain, irreducible element, prime element both are same. An element is irreducible if and only if it is prime. Did we do similar kind of problem? So here 2 is the irreducible element and 2 is the prime element here. Accepted? We know that 2 is a prime number. Now whenever you take an example, we can correlate all the results on one example. So this is all we talk about the factorization. So if you take the negative integer, it is also possible. Suppose you have taken minus 42, let me say. So here 42 is a positive integer. So for 42, you can have the prime factorization like 6 into 7, nothing but 2 into 3 into 7. So if you consider minus 42, this is nothing but applying minus to each of the values. These are irreducible things. So you can take the positive as well as you can take the negative. Whatever the case, factorization is possible. So how to prove that UVFD need not be a PID? That is our question. UVFD need not be a PID. Is that your question? Or the definition where each PI is an associate of QJ? Is that your question with regard to definition? Tell me. Yeah, second condition of UFD. So whenever you write the factorization, what I am saying here is, this is one type of factorization, this is another type of factorization. Both are equal for the same element, accepted? We can write it as P1, P2, P3. Here you can write it as Q1, Q2, Q3. Agree? Now see what happens. Here we are saying that Pi is an associate of Qj. What does it mean? If you take a value on the left side, this must be equal to some number into a value on the right side. And whatever this value, it must be a unit. So what is meant by unit here? If Pi is a multiple of Qj, this multiple value is nothing but having inverse. So if you consider Z plus dot, what are the units in Z plus dot? They are nothing but 1 and minus 1. There are no other units at all. So if you take 7, on the left hand side, the indication is P1. I will write P1 is equal to 1 into Q3, where 1 is a unit. 7 is equal to 1 into 7. Did you understand that? Is it fine now? So P1 is equal to 1 into Q3. Actually, you have taken Z plus dot. If you take any other different ring, there you can find the associates. There you can find the associates, that I will say. Now, let us take one more discussion on this concept of UFD. So, you take the context of Z root of minus 5. So, we know that it is an integral domain, but it is not a UFD. Just now you have asked how to prove the second condition. For that I am taking this example. So what does it mean? If you take an element having two factorizations, then one element cannot be a multiple of the other on the right hand side. That is a practical thing. So here you take that 46, this is nothing but 2 into 23. You accept it all? This is an irreducible element. This is an irreducible element. Yes or no? Do you accept or not? So, for the same value 46, I can write one more configuration that I am able to mention it as 1 plus 3 root over minus 5 into 1 minus 3 root over minus 5. So if you multiply these two, you will get the same value 46. Do you agree? So for a single number 46, I have given two representations. Just now you have asked. So this is the thing that 2 into 23 is equal to 1 plus 3 root over minus 5 into 1 minus 3 root over minus 5. So here on the left hand side you have different values. On the right hand side you have different values. Now I will prove that 2 cannot be a multiple of anything on the right hand side. So here you should get a unit. This case will not possible. So one element cannot be an associate of another element on the right hand side. That you can cross verify. Because you cannot find a value such that 2 is a multiple of the other thing on the right hand side. Do you agree or not? Because if you have a doubt, you can check, because 2 is an irreducible element. You cannot reduce it further. 2 is an irreducible element. Because I think on the same set z of root over minus 5, we have solved one problem that I think I have taken 3. 3 is an irreducible element, I think I have taken there. Did you observe? I have taken a problem on z of root minus 5. So using the same technique here, you can prove that 2 cannot be written as product of something here. You cannot get a unit here. That I will say. 2 is not at all associate of this. So this is one good example. So immediately you can ask one question that how you have taken 46 as an example presently. It is very simple. So the simple example is you take two prime numbers and consider the multiple, the product. Let me say I have taken 5 sevens 35. Now check that is it possible to write 35 using this type of notation? Is it possible to write or not? That you can check for it. That's all. Okay. Not only 46, you can take any kind of example. The simplest way is to choose like that. So this is one example that an integral domain which is not a UFD. I think this is also asking for 10 marks question in the exams. So to prove that 2 is not an associate of the element, you simply copy and paste the previous class proof where 3 we have done that under z of root over minus 5. The same proof you can reproduce that here. Now I want to discuss one interesting result on UFD. We will discuss on it. So if you take a unique factorization domain R, then every irreducible element is prime. And also prime element is irreducible. Both are true in a unique factorization domain. Prime element is irreducible, irreducible element is prime. So based on the previous year question, this result is asked. Every irreducible element is prime. Please show the result. Right? Now let us go for it. So if you say that A is an irreducible element, let us take. So from the very definition of irreducible element, A is a non-zero value and A is not a unit. A is not a unit. Now our intention is we have to show that A is prime. So what is the definition of prime element? Whenever A divides a product, we have to prove that either A divides B or A divides C. This type of situation we have to build. Then A will become the prime element or prime value. So let us take that A divides BC. Since A is a divisor of BC, immediately you can say that BC is equal to A into some number, say this is K. Say this is K. Now, whenever you write B and C, where B and C are elements in the ring, they have different possibilities. B may be a unit, C may be a unit, or both are not units. Whatever the case you consider, always we should be able to prove that either A is dividing B or A is dividing C, because A is dividing the product. Then A becomes the prime element. Okay? Did you get the strategy? Please take a note of that and confirm. Are you clear or not? Fine. Have you noted this, all of you? Okay. Now, if you say that B is a unit, what is meant by unit? B will possess inverse. So this relation, you multiply both sides with B inverse. Then you get that C is equal to B inverse AK. In other words, B inverse K into A. Accepted? So you have written C as a multiple of A. Therefore, A divides C. Agree? Agree or disagree? Similarly, you take the other case. If C is a unit, again, you multiply the relation both sides with C inverse. Then you get that B is equal to AKC inverse. So this is nothing but B is equal to A into some value. So B is a multiple of A. Therefore, A divides B. Now what happens if you consider that A is dividing the product, and in the product, if at least one value becomes the unit, automatically A is dividing the other element. So A satisfies the criteria of a prime element. Clear the step? Please check it. So if you get confusion with the representation writing like this, I will present it in the other way. Just like a small diagram that gives a good idea for you. So the thing what you are doing is A is prime. This is our task. So for this, we have started that A divides BC. So immediately you can say that BC is equal to AK, where K is a number. So here you are taking the possible cases. If you take that B is unit, so this equation, both sides you multiply with B inverse, then you get that B is equal to A into KB inverse. Therefore, A divides B. If you take that C is unit, then both sides you multiply with C inverse, you have that B is equal to AKC inverse. So B is equal to A into something. Therefore, what I got here? Sorry, C is equal to A divides C. Yeah. Therefore, A divides B. Because you are multiplying with B inverse, B gets cancelled. C is equal to. So this is the case. Now the third case is, let us take that BC, both are not units. Now in this case, we are going to prove the result. Now, I am confirming that in BC is equal to AK, K is not unit. That I am saying. Please understand one thing. Whenever you write A is irreducible, one of the element will be unit. You cannot always confirm that both are units. So whenever you write that X is equal to product of two values, in that one value should be unit always, as per the definition concerned. Let us think in a small way. If B is unit means, as per the definition of irreducibility, I am saying, since A is irreducible, either B will be a unit, C will be a unit, and both are not units. So you are saying that since it is irreducible, if you consider the product, one value should be unit. It is by default. That is what we are asking actually. Right? So please understand, you are understanding that B and C are separate values. Here, A is dividing the product, the result. Please understand. And the concept of irreducibility says that if X is irreducible, X is written as product of two values, in that one must be unit. That is compulsory. Here, we are talking about the division. We are not saying that A is equal to BC. Please understand. Did you get the whole idea? Right. Any other questions, please? Thank you. So, as we have taken that BC is equal to AK, K is not a unit. I am assuming this statement here. Now, since we have taken a unique factorization domain, for every element, we can write the product of factors. So I can write B as product of values P1, P2, so on, Pm. C as product of values Q1, Q2, so on, Qn. You have taken that A is irreducible, so you cannot write factors for it. A itself stands alone. K is not a unit, so you can write factors for K. So K is equal to product of factors R1, R2, so on, Rn. As we know that these two values are equal, substituting here P1, P2, so on Pm into Q1, Q2, so on Qn is equal to A into R1, R2, so on Rn. I have taken M, N, say this is L. Okay? Did you agree? The factorization condition? Right. Now, in the factorization, whenever one element has two representations, one value should be an associate of the other. So here, if you take that, A must be an associate of one of the P values, or A must be an associate of one of the Q values. Agree? The definition of UFD. Yes or no? Right. So, if you say that A is an associate of one of the values of P, you can say that A is equal to some unit U into Pi for some I. It means that A is written as product of Pi. Sorry, A is written as a multiple of Pi. So immediately we can say that A divides Pi. Accepted? Yes or no? So immediately we can say that A divides the product. So without having any confusion, let us say A divides the first element P1. I mean, A is an associate of the first element P1. So this is nothing but A is equal to U into P1. So A is a multiple of P1. Therefore, A divides P1. So since A is dividing P1, A will divide any product which involves P1. Therefore, A divides P1, P2, so on Pm. This is nothing but the value B. Therefore, A divides B completed. Similarly, if you know that A is not an associate of all these P's, then definitely A must be an associate of one of the values Q. So let us say that A is equal to some unit into Qj. A is an associate of Qj. Immediately A will divide the product involved Q's. Therefore, A divides C. So if you say that K is not a unit, automatically either A divides B or A divides C. Therefore, A is the prime element in the UFD. Proof is complete. Is it clear? The idea. Right. Now, our main idea is how can we confirm that K is not a unit? If you prove that K is not a unit, automatically this total result holds good. The proof is a genuine proof. Now, let us prove that K is not a unit. So, how do we prove that? If K is a unit, what happens? Let us prove it. So, you should get a contradiction. So, we have the condition BC is equal to AK. If K becomes a unit, what happens? What is meant by K becomes a unit? K will possess the inverse. So this thing, you multiply both sides with K inverse. We have BC K inverse is equal to A. So in other words, A is equal to B into CK inverse. Now, as you asked earlier, the same situation arises. Since A is irreducible, in the two things, I have written A as product of two values. So, in the two things, one value must be definitely a unit because A is irreducible. Since B is not a unit, because I have taken three cases, B is unit, C is unit, B, C both are not units. Right? Are you clear? Since B is not a unit, the only possibility is this thing must be a unit. So what does it mean? It will possess inverse. So what are the inverse of it? Ck inverse whole inverse. What does it mean? Applying the condition K inverse whole inverse into C inverse. This is nothing but Kc inverse. So whenever you use the word C inverse, it means that C inverse existed. Inverse of C existed. It means that C is a unit. Again, it is wrong because you have started that both B and C are not units. So whatever the case you take, you are getting a contradiction. So K should not be a unit. Sorry, yes, K should not be a unit. This thing will happen. That's it. So this is the proof that every irreducible element is prime. So this question was asked in the previous year papers, that's why I have chosen that. Right? So please take a note of that. So at this point, I want to conclude our discussion here. And tomorrow we will meet with the new concept that finite fields, or we call it as field extensions. So this will be interesting. There you can find many problems under UPSC pattern. What kinds of questions are asked under finite fields? Okay. So in the next upcoming session, we will deal with that. Finite fields. Is it clear to all? Right? So let us wind up here now. If you have any other doubts with regard to class session, you can ask. So I hope that we will finish this part of abstract algebra by February 1st. That I will mention for you. So upcoming Wednesday or Thursday, we are going to finish this part of abstract algebra. So I sincerely request you to go through any one book, one standard textbook, you go for it. Either abstract algebra by S. Chand or Sham series or V.K. Khanna, S.K. Bhamri, any one good book you follow. As per the syllabus norms, you refer the examples and problems given on that. That is sufficient for you, right? So I will inform you. So if I am going to continue, I will take the concept of mathematical methods, I mean numerical analysis, or Venkana sir will continue the class. I think so far Venkana sir is not at all taking the classes for your batch. I hope so. He didn't start his sessions, right? Am I correct? So may I know from what topic you have started in this batch? From what topic onwards you are in this batch? Are you coming from linear algebra onwards or analysis onwards? So you are from abstract algebra only. That is fine. Linear analysis, linear algebra. So you started by vector calculus. Fine. So is numerical methods covered to you or not at all covered? Fine. So just let me know how many of you already covered numerical methods in the class session, numerical analysis, or no one has covered it. No one has covered it. Then done. So we go in the cyclic order. So Venkana sir will resume the classes, or myself take the easiest topic, that is numerical methods. There we can complete our portion. So that is the upcoming plan. Clear? Right. So are you comfortable with the so far discussion made on abstract algebra right from the beginning? Right? Thank you. Then let us wind up here now. So if you want to add anything, you can add for today's session. Right. Thank you, all of you.